Hello, ladies and gentlemen. Welcome to our screencast for the course Internet of Things. My name is Roel van Tempel, and I will cast the first part of the presentation, and my partner Ruud van Vijfeijken will cast the second half. The topic of this cast is about the challenges for IoT protocols in domestic environments. So in the 6 circles you can see what we're going to talk about. I will first talk about the goals of the screencast and give you an introduction to the topic. Then Ruud is going to look with you at a subtopic that discusses an IoT protocol in more depth. This protocol tries to overcome one of those challenges, and from this subtopic results are evaluated and a conclusion is made. We will end the cast with several interesting literature suggestions that give more info about this topic. So yeah, let's start. So our first goal is to give you a better understanding in the challenges that protocols in smart homes have. The second goal is to give you an in-depth view of one of those protocols that is used in smart homes. So we want to show you how this protocol combats one of those challenges and hereby increases performance. And then our third goal is to evaluate these results and give you conclusions based on these evaluations. And our last goal is to provide further readings for viewers that find this topic very interesting and want to read more about it. Now we're going to our introduction. So, what actually is a smart home? So the idea of a smart home is to automate your home by connecting all kinds of electronic devices together. And all these devices can be controlled with apps from your smartphone. And devices can even work together, so they form a smart and automatic home environment. So what kind of devices can be connected together in a smart home? Let's take a look in our living room. What we see here is a typical smart home living room. In this room, every device is controlled remotely from your smartphone. So you can, for example, change the channel of your TV, or you can control the lights above the TV. You can monitor the security from cameras and motion sensors, and you can regulate the temperature from your heating system, and even close or open the windows in your home. And this can all be done from your smartphone. And as you can see, even in this living room alone, there can be dozens of wireless devices connected to each other. Then where in this story do IoT protocols fit? So IoT protocols are responsible for communication between all these devices. So these protocols define how these devices communicate to each other. However, connecting all these devices together in smart homes poses multiple challenges for a protocol. As we saw in our living room example, there can be dozens of devices in a small area trying to communicate to each other. The more devices there are in a small area, the more interference this will give, and thus also more latency. Devices will have to wait for each other before they can access the wireless medium. Another challenge is that these devices are often low power to save energy. Low power devices have a smaller communication radius and a slower communication speed, which makes it much harder to transmit data fast to other nodes. Another challenge is the overhead of conventional internet protocols. For example, an IPv6 packet is approximately 1280 bytes large, with a fair chunk of overhead. Such a packet takes a long time to transmit, especially for low power devices. So large overhead leads to lower packet rate and more latency. Now that we know more about the challenges in protocols, we see that the traditional web-based communication is not suitable for a smart home. In this picture you can see that the web protocol stack has a size of hundreds to even thousands bytes of data, while an Internet of Things protocol only has a size of tens of bytes of data. So special IoT protocols are designed to optimize communication efficiency that is required in a smart home. So how is the IoT stack built up? An IoT stack consists of several layers, each with their own tasks. The higher up the layer, the more abstract is the communication between the nodes. So the most top layer is the application layer. The application layer is responsible for end-user application interactions in the network. So this layer is very abstract and does not deal with, for example, actual data bytes. Then we have the server's discovery layer. This layer allows automatic detection of devices or services that are offered by these devices. So you can compare this to, for example, DNS that translates a website name to an IP address. Then we have the infrastructure layer. This consists of several layers that are responsible for routing between devices and, for example, managing the access of a wireless medium between transceivers. The most bottom layer is the influential layer. This consists of standards for security in the network, but this layer actually encompasses all the layers. So here you can see example IoT protocols that are actually used in smart homes. For our subtopic, we are going to look at the routing protocol. This protocol is called RPL. Now that you have some insight in the challenges of IoT protocols and the IoT protocols that exist, we want to discuss a paper that looks at the interference when using RPL. And of course, interference is a big challenge in smart homes. So I'm going to give the word to Ruud, who will tell you more about this.
Hello, my name is Ruud from Vijfeijken and I will be your host for the second part of the screencast. In this part we're going to take a look at the subtopic. The subtopic is performance of RPL under interference. As my colleague told before, RPL is an infrastructure protocol, more specifically a routing protocol. And as he also told you, there are a lot of interferences in a smart home. So we're going to take an in-depth look at how RPL performs under interference from all these other wireless signals. To do that, we're going to first take a look at RPL and how does RPL work, and then we're going to take a look at an experiment and analyze the results of this experiment and draw some conclusions from that. So first up is RPL. RPL is a routing protocol for low power and lossy networks based on IPv6 and standardized by the IETF, or the Internet Engineering Task Force. It is designed for wireless networks such as sensor networks and for smart homes and offices that use mainly low power devices. The network can have different structures, from for example multi-point to point, point to point, or point to multi-point. And what I mean by that is that multi-point to point means that there are a lot of small devices that all send their data to one specific device, and point to point is just one device to one device, and point to multi-point is the vice versa of the first one. So to take a look at how RPL exactly works, we're going to go to the next slide. RPL has a structure of a destination-oriented directed acyclic graph, or for short DODAG. A DODAG can be seen in the picture before you. It has a structure which has one root, the DODAG root, as can be seen, and all the others are other leaves or routers. The root is the parent of the two nodes that is below them. Every leaf from a parent can see its parent, but it cannot see its own childs or leaves. So the structure is exactly as the arrows indicate. That's exactly what one node sees. So the bottom left node only sees the two nodes that are on top of it. And this way you get some kind of tree structure in which you send your messages to the root and vice versa. There are 4 kinds of messages in a DODAC network. The first one is DO, or DODAC Information Object. It keeps the rank of the node, so in which level it actually is. So for example, if you take the root 0, then the nodes below it would be 1, and then the nodes below it would be 2. So the rank of the DO is used to determine the distance of each node to the root based on specific metrics. In this case, in case of my example, it was the hierarchy. The DO also is used to choose a preferred path to the root to make the directed acyclic graph. The second message is the DAO message, or the destination advertisement object. This is sent by the nodes to their parents or to the root to acquire the destination information towards the parents it wants to send messages to. So for example, the right bottom node wants to send messages to the root, so it sends out a DAO message to make the link. The bottom one, DAO acknowledge is an acknowledge to the DAO message. So in that case, it can be confirmed that the DAO link is being laid. And the last type of message is the dis message, or in full length, the DODAC information solicitation, and it's used by a node to acquire DO messages from a reachable adjacent node. So one sends out a DO node, this node, and gets a DO node, gets DO messages back, and in that way it can discover the network and know what its parents and neighbors are. When one makes an RPL, the root is the starting point. The root sends its location using a DO message to all low power lossy network levels. So in this example, the rank 1 and rank 2 of the nodes. At each level, recipients save the path to the parent node and propagate the DO messages. So rank 1 accepts the DO message from the root and sends it to rank 2, so, and so on if the network would be bigger. So in that way, the acyclic graph is being generated. Yeah. So to test how the interference of how RPL reacts to interference, an experiment has been held, and we're going to take a look at it now. Before you see the setup of the experiment. In this experiment, they deployed an application to monitor the power use of the computers in a computer lab. And the lab had around 23 computers arranged in 4 rows. It was just on the university, so they tracked the students that would log in on these computers to check email, for example, and do their homework. And the goal of the application, outside of course determining how much interference there was to track to monitor the energy used in the computers while just using them over a whole day. So in the picture you can indeed see the example sketched with only 2 computers, in which the wireless devices send the power readings over wireless using RPL to the base station. So the 23 computers that were mentioned before have a structure like in the previous slide, in which they send it to the root, in this case the base station, to collect the data and then send them back. Outside of RPL, there are also other IoT protocols in use. For example, there is a 802.15.4 from the IEEE in the physical and Mac layer. And outside of that, there is also a 6LoWPAN network in the network layer. So RPL isn't the only network, isn't the only protocol that is being used, but it's the main one here. Outside of that, there are 4 different setups in which this computer network is being used. The first is low interference, in which the nodes from the computer are run in a channel in which there is no interference, so there will be no interference from sending the power readings from the computers to the base station. The second one is normal interference, in which there will be a channel is chosen that overlaps with the Wi-Fi. So Wi-Fi can interfere, and on the Wi-Fi some standard apps are being used from the computers and stuff like that. So it's a normal office environment in which they run it. It's being run. The next one is mixed interference, in which in addition to only the Wi-Fi interference, also 2 nodes are being installed that are constantly spamming a message to each other. So it generates a lot of interference from those 2 nodes. And the last one is high interference, in which not an additional Wi-Fi app is being deployed. So there is a lot of interference from a different Wi-Fi that I run at 20 megabytes per second. So a lot of data is being sent. So there is a lot of interference. To check what the results are, we're going to the next slides. So we will go through each diagram of the results, and I will explain what is being shown here, and from that we're going to draw some conclusions as to how RPL is being influenced by different setups that I just mentioned. So our first results screen shows the PRR on the vertical axis and the scenarios on the horizontal axis, the low, normal, mixed and high. PRR is the packet reception rate, and it is the most common metric used to quantify how reliable a protocol can deliver packets to the destination. So the PRR, if you have 100% PRR, it means that one node the messages from one node always will arrive on the destination node. So that's in essence what you want. If we look at the graph, then the low interference is almost 100%, which is obvious because there is no interference, but the normal one already has some interference, and this is already lower. The red line gives the average, which means there is about 90% PRR, so 90% of the packets will arrive at the destination node. When we go to the mixed scenario, there's already a lot of more interference with those 2 nodes, and the PRR already goes down to around 75%. And when we go at high, it's around 10%, and that's really bad. Next to the packet reception ratio is the estimated number of transmissions that can be seen in this slide. The estimated number of retransmissions is how many times you send a message before it actually arrives, and thus generates the packet reception ratio that's being shown in the previous slide. As can be seen, when it's low, there is an average of 2 retransmissions with a reception ratio of about 100, so it's nothing bad there. But if you go to the right, you see that the amount of retransmissions is gradually increasing, and there are even more higher ones. So in normal, it already reaches sometimes 8, a lot of 4 and 6 too. Mixed, it's even higher, and when it's high, there are really a lot of retransmissions, and the worst thing about this is that the packet reception ratio still is only 10%, so even with such a lot of retransmissions, it still can't get there at all. So the RPL has a lot of problems with the interference. And to make matters even worse, there is also a control overhead that's being generated because of the number of retransmissions that are being done here. Because when RPL does not work well, it tries to find a better preferred path to the root or to its parent. So it sends out a control message to get a new path, or to switch itself from rank, or to discover a new path to make the network better, or to repair itself in some cases when links are being broken. So the next slide we show the control overhead ratio. This means that for the vertical axis shows the overhead ratio, and the horizontal axis shows the scenarios again. The control overhead ratio means that when, for example, with the low interference one, there is a 0.15. There are 0.15 control messages for each normal message that is being sent to. So you want that to be as low as possible, because when you look at the high one, there is also there's most of the time at least one control message for each message that you send. That means that you have as much overhead as that you actually send, and so there is a lot of interference, and it doesn't even get anything in the end because the packet reception ratio is still bad. But you can see that in the normal case it's around 0.3 and mixed is around 0.5. So for each packet that you send, 0.3 control messages are being sent, which is okay, but still not what you want. Now the last result we have is the excess parent change, and with that we mean the specific count of control messages, of control overhead, that is absolutely useless, because when you change your route, most of the time you do it because there is a better route available to go. But if the route is not there, and you stay in the same rank, so you don't come closer to the route or don't find a better path, then you actually didn't reach anything with your control message, and thus have a excess parent change that is not needed, and this causes even more overhead. And as can be seen, low doesn't have anything, normal has a little bit, but if you go to high, it's already between 30 and 60%. So 30 to 60% of all parent changes that are being done by the control messages don't deliver anything. It doesn't get any result. It still stays bad, which means that it doesn't get any good routes and links, and thus cannot get the messages where it wants. Now we move on to the evaluation of the results. When we think about it, 90% in a normal situation is not that good. It sounds okay, but it's not, because there are a lot of IoT devices that can't have any breakup at all, so they at least need something like 98, 99%. Because imagine if you stand before your door and it's snowing, and there is an IoT lock before you, and it doesn't receive the message because of all the interference, and you're standing there in the cold. It's not something you wanted. Now this is a kind of cheesy example, but there are some, for example, security devices that do not want any packet loss, so the packet reception ratio should be higher. And even when you increase that, and the number of IoT devices will increase in a smart house, it gets even worse. So something about that needs to be done. So to get a network to work reliably under interference, coordination between layers and devices is needed. So some kind of standard is needed over all devices. This is hard in practice because different standard bodies are responsible for standardizing different standards. It sounds kind of redundant, but for example, IEEE is about the low level from the network, and IETF is about the network layer and internet. And there are also different parties like Zigbee that have some kind of other standard. So there should be some kind of universal standard to get it better working. There are also other solutions to reduce interference from other sources. For example, there is a research about a Zigbee network that has interference from Wi-Fi networks, but to counter that, they add a bigger header and stuff like that to reduce the interference. The example of the paper can be found in further reading, and is interesting, and you should take a look if you want. Now, to move on to the conclusions. Explosion of devices in smart homes leads to communication challenges. As mentioned before, it causes a lot of interference. You have a lot of security you need to take care of. It just comes with a lot, and there's a lot that needs to be taken care of. Protocols in each layer are designed to combat these challenges. The RPL is made to make the applications work more smoothly, but as can be seen, it's not perfect yet. But it's also because it's all kind of pretty new, so it's still in growth. They are still making it better. Performance of routing layer protocol RPL under heavy interference is not so good, but there are solutions, as mentioned before. The possibility of lowering the interference. The further readings can be found here, and there's also papers that are used to in this screencast. We hope you like the screencast, and thank you for watching.